Support vector machines, or SVMs, are powerful and versatile machine learning models. They are used for both classification and regression tasks. SVMs are particularly well suited for classifying complex data with high dimensionality. In essence, SVM attempts to find the optimal boundary that separates different classes of data. This boundary, called a hyperplane, is chosen to maximize the margin between the classes. This maximizes the distance between the data points closest to the boundary. The points closest to the hyperplane are called support vectors, as they support the definition of the separating boundary. SVMs are known for their ability to handle datasets with many features, or high dimensionality. They are also effective in cases where the number of features exceeds the number of samples. SVMs can capture complex relationships in the data. This makes them suitable for various tasks, including image recognition, text classification, and bioinformatics. Imagine you have a set of data points, each belonging to one of two categories. For example, you might have data on tumor size and malignancy, whether benign or malignant. Your goal is to find a way to classify new, unseen data points based on this existing data. An SVM accomplishes this by finding the best hyperplane that separates the two classes. In 2 dimensions, a hyperplane is simply a line. In higher dimensions, it is a plane or a higher dimensional analog. The goal is to find the hyperplane that maximizes the distance between the closest data points of each class. This distance is called the margin. The hyperplane acts as a decision boundary. New data points are classified based on which side of the hyperplane they fall on. Points on one side are classified as belonging to one category, while points on the other side are classified as belonging to the other category. Not all data points are created equal in SVM. The points that lie closest to the hyperplane are called support vectors. These points are critical because they determine the position and orientation of the hyperplane. If the position of any other point changes, as long as it doesn't cross the margin, the hyperplane remains unaffected. Support vectors play a crucial role in SVM's ability to generalize well to new data. By focusing on the most important data points, the support vectors, SVM can effectively ignore outliers and noise in the data. This makes SVM more robust and less prone to overfitting compared to some other algorithms. The margin in SVM is the distance between the hyperplane and the closest data points of each class. A larger margin generally leads to a more robust classifier. This is because a larger margin allows the SVM to tolerate more variability in the data without misclassifying points. Think of it like this. If the margin is small, even a slight change in a data point's position could cause it to be classified incorrectly. However, if the margin is large, the data point has more wiggle room and small variations won't affect its classification. SVM aims to find the hyperplane that maximizes this margin, leading to a more robust and generalizable model. This concept is sometimes referred to as maximum margin classification. Section 5. Non-linear classification with kernels. So far we have only considered cases where the data can be separated by a straight line or hyperplane. However, in many real-world scenarios the data is not linearly separable. This is where kernels come into play. Kernels are mathematical functions that allow SVMs to operate in a higher dimensional space without explicitly calculating the coordinates of the data in that space. This is done by implicitly mapping the data into a higher dimensional feature space where it might be linearly separable. There are various types of kernels, each with its own characteristics and suitability for different datasets. Some common kernels include the linear kernel, polynomial kernel, and radial basis function, or RBF kernel. The choice of kernel can significantly impact the performance of an SVM, and selecting the right kernel often involves experimentation and domain knowledge. Section 6. Advantages of support vector machines. Support vector machines offer several advantages that make them a popular choice for various machine learning tasks. Firstly, they are effective in high-dimensional spaces. SVMs are particularly effective when dealing with datasets with a large number of features or high dimensionality. They are also robust when the number of features exceeds the number of samples. Secondly, they are memory efficient. SVMs are memory efficient because they only need to store the support vectors, not the entire training dataset. Thirdly, they are versatile. SVMs can be used with different kernel functions to model both linear and nonlinear decision boundaries. making them adaptable to a wide range of datasets. Lastly, they are robust to overfitting. By maximizing the margin, SVMs are less prone to overfitting, especially in high-dimensional spaces, compared to some other algorithms. Section 7. Applications of support vector machines. The versatility and effectiveness of support vector machines have led to their widespread adoption in various fields. For example, in image recognition, SVMs are used in image classification tasks, such as recognizing handwritten digits, detecting faces in images, and classifying medical images. In text classification, SVMs are employed in natural language processing tasks like sentiment analysis, spam detection, and document categorization. In bioinformatics, SVMs have applications for tasks such as protein structure prediction, gene expression analysis, and drug discovery. And in financial forecasting, SVMs are used in financial applications for stock market prediction, credit risk assessment, and fraud detection. Section 8. Conclusion. Support vector machines are powerful and versatile machine learning models that excel at finding optimal boundaries between data points. Their ability to handle high-dimensional data, leverage kernel functions for non-linear classification, and maximize the margin for robustness makes them valuable tools for various applications. From image recognition to bioinformatics, SVMs continue to play a crucial role in advancing the field of artificial intelligence and solving complex real-world problems. Section 9. References. Jaron Aurelian. Hands-on machine learning with scikit-learn, Keras, and TensorFlow concepts, tools, and techniques to build intelligent systems. O'Reilly Media, 2019. Cortez, Corinna, and Vladimir Vapnik. Support Vector Networks. Machine Learning 20.3, 1995, pages 273 to 297. Burgess, Christopher J.C. A tutorial on support vector machines for pattern recognition. Data Mining and Knowledge Discovery 2.2, 1998, pages 121 to 167.